Hello to new episode. Firstly, I'm sorry that this one took me so long. Today I wanna share with you time-lapse of dynamic loader creation for cortex-m microcontrollers. This episode is quite long and it was split into chapters, so you can watch only parts that you are interested in. Let's start with few slides about dynamic loading. From definition, dynamic loading allows to run application from any address in memory space. Normally, when building executable for microcontroller, all addresses are known at build time, which leads to a situation that executable must be placed at exact memory address inside memory space. But within Yasld and also inside operating system, I want to put many applications that I can select to run. Also, in the future, I want to extend functionalities of Yasld via modules, but this will require to add also dynamic linker, not just dynamic loader. When I was working on first implementation of dynamic linker for microcontrollers, I found a project called UDinLink, and I took some inspirations from it. So if you are interested in those topics, it's worth to check GitHub repository from that project. In the future, I'm going to extend dynamic loader to full dynamic linker, which allows interoperation between dynamic libraries and executables. For regular computers and also for mobile phones, microprocessors contains memory management unit, which is dedicated for dynamic linking or loading. The purpose of that part of hardware is to translate virtual addresses to the real physical ones. And thanks to that, any executable can be built with known virtual address map, very often starting from 0, and then relocations are done by memory management unit. But most of the microcontrollers doesn't contain MMU, so we need to find a way how to create dynamic linking without that piece of hardware. To show you that concept of position-dependent code is easy in fact, I prepared simple animation. Even we have very simple source code example. We just return some value from memory. After compiling with ARM toolchain, I disassembled that part of code. In this animation, register view shows current register states. Only ones that take part in example. RAM view shows memory at given address. Disassembly view shows regular executable on the left side and executable built with fpic on the right side. Both was compiled for exactly same hardware. Let's see example from the left side. Important thing to note is code in memory space placement is clearly visible. All instructions were placed at addresses around 8 million, of course in hexadecimal. First instruction loads register R3 with value from program counter offsetted by some value. PC relative addressing has formula to calculate exact address. It is sum of program counter value, constant value 4 for dump instruction set, and offset value from instruction. Then the result from that sum is aligned to 4 bytes, rounded down if necessary. So I'm setting two last bits to 0 using binary mask. Offset given to instruction also must be a multiply of 4. Changes between steps were marked with green color. Then register R0 is loaded with data from memory pointed by address inside register R3. As you are able to see, register R3 contains direct address to access data from RAM memory, and function returns. Position-independent code has first difference that code addressing no longer follows hardware address mapping. It is compiled to be able to place at any address in memory map where execution is allowed. Let's place this application at address starting from 8,100,000, then PC counter is started accordingly. Position-independent code requires more instructions to do same task. That's why it's not used at first place. Register R9 is filled by dynamic loader and points to start of offset table. Also, all entries inside offset table are filled by dynamic loader. First instruction moves register R9 to R2. It's necessary for ARM architecture version 6M, where higher registers are not exactly same as lower ones. Then R3 register is filled with index to offset table entry using PC relative addressing. Formula is exactly same as in first example. Register R3 is going to be filled with data from memory pointed by R2, which is address of table start, plus offset to get entry. Now, register 3 contains address to data, and next instruction loads that data to register R0, and function returns. This time, there was no direct addressing. All memory accesses were PC relative or using offset table. And this is how it works. That's all in fact. Any magic here. Advantage of that solution is that I can extend system functionalities during lifetime without replacing whole firmware inside. Also, I can use advantages of shared libraries and load modules from external memories that are not mapped. Just I need to copy them to empty RAM memory. Of course, it has also cost. Big code is larger, requires additional metadata to process relocations, and additional components that will do it, like dynamic loader or dynamic linker. ARM-run EAB toolchain already supports position-dependent code, with use of flags. Important ones are fpeek, which enables position-dependent code, single peak base, which treats peaks register by default R9 for non-EAB as read-only, so compiler won't generate wrappers to manage register R9, and moves responsibility to runtime system, for example to dynamic loader. No peak data is text relative, separates text and data section, which is necessary if only data is copied to RAM, and mpeek register. If there is a need to change default R9 register, we can use some other. Since we know how position-independent code works, let's see major steps that dynamic loader must do to load executable. Let's assume that we have executable inside flash memory with given layout. Application starts with metadata block with informations necessary for dynamic loader, to process relocations, and to prepare executable to run. Application text section is just binary code. Application data block is initial state of data. It is necessary to copy that to read and write section inside memory map, basically to RAM memory. Dynamic loader starts with parsing metadata for application, then copies data or code and data to RAM. On diagram below there is RAM layout for this example. Inside RAM, there must be allocated space for offset table, which must be filled with addresses calculated based on code, data position, exported or imported symbols. Generally, addresses of memory accesses must be resolved. GCC toolchain might generate static relocations for read and write sections, so dynamic linker must also fix these relocations inside RAM. I'm calling them data relocations. Those relocations are calculated based on data section position and metadata. Offset table must be pointed by register R9, and code is executed on some entry point. I'm going to use main function as entry symbol for executables. To build metadata block, it's necessary to get relocations, and this can be easily achieved with use of single flag for GCC. Relocations are exported to ELF files, but R files are too big for microcontrollers. So let's design our own format for metadata. Let me introduce Yasld, yet another simple image file format. I'll try to do it fast. If you want more information, look inside my project on GitHub. We need to store data about file type, CPU architecture, binary code, imported libraries, imported symbols, exported symbols, and all relocations needed to run. Architecture section is going to be used in future to address differences for microcontrollers other than cortex-m 0+. Imported libraries is list of libraries on which given module is dependent. Relocation tables keeps relocation entries. It is splitted for symbol table relocations. In this video I'm unnecessarily splitting relocations to exported and imported, which duplicates data in relocation tables and symbol tables. I will fix that in dynamic linker part. Local relocations where informations about symbols are not needed, and data relocations for relocations that must be done inside RAM. Padding and alignments are used to easily parse on microcontroller side. Symbol table relocations uses index of offset table and offset to symbol table entry. Local relocation uses index of offset table, section flag if relocation is towards code or data, and relocation offset. Then data relocations uses address to be changed, and section and address from where get value. Symbol tables for exported and imported symbols. Each symbol table entry contains section and offset to symbol, followed by symbol name and coded in ASCII. Text and data contains actual executable or library. Last thing is that ARM non-EAVI toolchain doesn't contain position-independent libraries, like libc, libstd, C++, and others. So I need to provide own toolchain. Otherwise, for example, floating numbers won't work. So let's start actual work. I created Python script for building toolchain. To be honest with you, in video this is first step, but in reality it was last. Firstly, I compiled toolchain manually many times to produce working binary. My plan was to create script that parses recipes. Each recipe represents steps necessary to build given component. For example, GCC or newly. During manual building, I realized that it may be necessary to rebuild single component. So I wanted my script to support filtering. Let's freeze for a while and see interface for recipe. I think all recipes should be doable within 5 steps: fetching, unpacking, configuring, building, and installing. When filtering of components was implemented, I started implementation of recipes. I stored all of them in subdirectory recipes, but there is also file with base class. So recipe file exports flag is build recipe to determine if this is recipe or not. Base class is doing generic tasks, like hash verification, and non-generic steps were implemented in specific recipes. First step was to initialize base class with source link, and checksum for file from that link. Then it was time for unpacking file. It's not visible on video, but I spent a lot of time to add progress bars for that step. I just wanted to know that files are unpacking and not stacked on some file. Configuration step was implemented nextly. This one is first, which differs between components. So each of them must implement its own version. For GCC, this step is most important. Configuration selects options and flags for toolchain building. It's a place where flags for position-independent code must be added. Build step is fairly simple. Only flags needs to be passed for the aggregate libraries and make called. If you are interested from where I got base for configuration, I use recipe for Arch community repository. Link is in the description. For embedded toolchains, there is usage of nano libraries, which basically means that it's possible to provide regular full-size libraries and highly optimized nano libraries, and then select needed by specification file. Last thing was adding dependencies between components. It's necessary because some components might require others. For example, to build newly libc, I need cross-compiler built by GCC. Let's verify that part. It was fast? Not really. And I had to rebuild that many times. Since I cheated a little bit with creation of script at end, as was able to verify toolchain correctness with already implemented dynamic loader, together with its tests.
Yeah, man, we did it!
As last step, I added stripping of host executables to reduce toolchain size. It's necessary because I want to keep toolchain on GitHub. Nextly, I created Docker container, which contains newly created toolchain. Docker container will be useful for GitHub Actions. With working environment, it is time to start project creation. First 3 regular CMake work similar to my other videos. But there will be one challenge. I'm going to implement tests in simulated environment. So I need to compile project with using at least 2 toolchains, which is not easily supported by CMake. One toolchain to build dynamic loader for microcontroller, and second to build modules for that loader. So for example, Renode GCC toolchain and my Yasld toolchain. In meantime, I started implementation of MKImage script. Its responsibility is to convert ELF files to my own format, as I described in theoretical section. Also added unit testing framework for that script. MKImage uses configurable logger. In normal builds, it shouldn't be used. To not overflow logs, it may generate a huge amount of information. But it is necessary during issues debugging. For regular builds, at least for first usages, maybe I will redirect logging to files. Then I started actual logic implementation, which starts with processing ELF file. But to get idea how to process such file, I need to get one. Since I choose Renode to write tests in simulated environment, I need to select microcontroller that is supported by Renode. Basically, I need any cortex-m0 microcontroller. Thanks to that, dynamic loader should work on MSPC out of the box. I selected STM32 board and I chose libopencm3 as SDK for it. It is lightweight and very easy to use. Now it's time to tell you how I added support for multiple toolchains inside single CMake project. I use CMake external projects feature, but instead of adding external project, I'm adding same project sources, but different flags. And thanks to that flags, I'm able to, for example, not stuck in recursive loop, and also to configure for different targets. In the future, I'm also going to use it when I will be porting dynamic loader for other architectures. Then I create a toolchain file to configure Renode GCC and my Yasld toolchain. Yasld toolchain file uses environmental variables to get paths where toolchain lives. Now you see continuation of system-level test project creation. Of course, there were bugs with external project usage. To be honest, bugs with external projects and dependencies between them are going to pop up for entire video. I also created macro to easily add testing targets. It will be used to combine dynamic loader executable with modules. Build flags were created to propagate flags for target dynamic loader building and for modules. Finally started source code implementation. System stubs contain symbols that must be provided to new libc library. They mostly wraps OS calls and heap management, which I actually implemented using static variable. Is probably the simplest implementation of heap. Also added write implementation for debugging. As a starting point, it's enough to print something. For STM32 and GCC, it's necessary to provide linker script, which tells linker about hardware memory mapping. OpenCM3 library delivers base script, so it just needs to be filled with memory map. Then I confirmed that the executable inside Renode simulated hardware is working and printing my awesome print. To don't write each step necessary to execute inside Renode each time manually, I created Renode script. and I created it as a template file to use it by many modules and many tests. Now it's time to implement the first simplest possible test. Let's pause for a while. I'm using here the register_st function. I don't know what happened, but for some reason creation of it wasn't recorded. It's a CMake function that wraps a Python script. And the Python script creates a YAM file with the tests that will be executed by Renode. Thanks to the simulated environment, the executed binary is exactly same as for the real hardware. Tests are a combination of host that contains loader and modules. A specific test uses a specific test host implementation and specific module for that test. The test loader uses the normal variant of libopencm3, and the module uses the position-independent version. I tried to share the Yasld package manager between sub-projects, but it created some problems, and it will be changed in the future. The Yasld disable test variable is important, because it prevents an infinite loop. Since I'm adding the root of project using external project add inside its own child. In the meantime, I copied the system stubs with a few small changes. Since I'm implementing a dynamic loader in this part, I'm not able to share code between the environment and the module executed inside, so each executable must be standalone. The system stubs were exported to a common library, since they will be used by most or even all tests. This proves that I was building from time to time. I was referring to the Yasld executable flags target, but I didn't define it yet. Now it's time for that. That target defines flags for position-independent code and disables C++ features that are not supported yet, mainly some complex ones like exceptions or RTTI. I added an empty main function to have everything necessary to build the module. And we have successful launch! Some symbols are position independent and thus have got rel relocations. Now it's time to combine the loader and the module. I'm using a custom command that first creates a binary file from the loader executable, then it changes the binary to a determined size. The purpose of that is to place the module at address that is known for the loader. Thanks to that, I don't need a file system or other complex implementation for managing modules, and a custom target that combines the loader executable with the module in YASI format. Since I changed executable format from ELF to pure binary, I had to update Renode scripts. And of course, I have to generate the YASI file itself. The conversion function just calls the Python MKImage script. The custom target ensures that YAF file is tracked by CMake. The MKImage script must export the file, which was not needed until now. I forgot that I commented out the module name during debugging. It seems we have combined executable and even some tests were executed. But we don't have MKImage implementation yet, so in fact those tests did nothing. I started from ELF parsing. To make it easier, I'm using external library called pyftools. The purpose of this class is to filter only necessary information from ELF file, so it fetches symbol tables, sections, relocations. Of course, I'm taking only fields that will be used by MKImage. The ELF parser class only parses the file. It doesn't do any validation of data. That validation will be done by MKImage in places where it's needed. Starting from fetching a section, MKImage validates that necessary section exists and that data section is placed after the text section without any gap. Let's test the first real MKImage step. Modules were planned to also contain data and BSS sections. Data contains initialized variables and they must be copied to RAM by loader, and BSS contains uninitialized variables, so only its size must be passed to the loader. Then it's time for the linker script for the executable module. It differs from regular linker scripts for microcontrollers. Addressing starts from 0 and contains only a linear memory block, which I call image. Text section must be followed by data section, but this is actually limitation in my implementation. It probably can be implemented other way. Then it is followed by BSS and global offset table, where global offset table stores relocations and will be removed by MKImage script to reduce size. Those relocations will be replaced to own format. Let's compare them. The simplified script for the dynamic loader is on the left side, and the example regular script is on the right side. The only real visible difference here is the flat virtual memory space in the dynamically loaded executable, starting from 0 with unconstrained size. Time to test the memory layout with the new linker script. Success! And in the log we can see that MKImage extracted text data BSS sections correctly. I added a CMake dependency to the linker script to enforce tracking changes inside that file. The next step was symbol processing. I removed the $T and $D symbols since they are related to mapping between ARM, TAMP, data. They are used by ARM toolchain, so they are not real symbols that I'm interested in. Then for the executable, I search for the main symbol and change its visibility to ensure that it is an exported symbol. It's my entry point for the executable, so must be visible. It's important to make useful logs, and there is always a lot of bugs in early implementation. Let's add generalization for dumping symbols to support visibility separately. The most important part: relocations. I started with a relocation set that keeps track of relocations and counts them. It's necessary to correctly count relocations to build the offset table. Local relocations are internal for the module. Each local relocation must be resolved independently, even for the same symbol. Thus, access is relocated, not code or data. I created an add relocation function for symbol table relocations. Those can be done once per symbol, so I'm omitting already added ones. To be honest, I think that in all cases, or in most cases, they are just pointers. Data relocations are done in place. They occur in RAM memory, where reading and writing is possible, so they can be changed in runtime. Thus, they don't touch the offset table. Now I'm going to process relocations. But how do I know how to process them? Some of them are already done, since they are program counter related, which can't exist in read-only sections of relocatable modules. This is hardware-related knowledge. In this particular case, CPU architecture. For 32-bit ARM, there are two great sources of that knowledge. Both of them I linked in the description. The first one is the ARM ABI ELF specification, which is a very detailed documentation of ARM ABI. Let's search for the relocation section, and here we can see most of the information about relocations, such as type, whether they are towards ARM, TAMP, code or data, and relocation formulas. There is a comprehensive section on how to calculate them, but for most cases, I need information on whether relocation is PC relative or not. And there comes the second web page. It is a relocation description for Android system. And there I can find most of the information that I need. Mainly information on whether relocation is PC relative or not. Most of the position-independent code will contain ARM got relocation, which I need to process. It is an offset table relocation. It's an offset table relocation and may be related to a local symbol or a symbol table. For unimplemented relocation, let's raise an error. As such, executables won't work properly without updates inside MKImage. Next, I added data relocations, which in most cases will be ARM ABS32. I'm calculating the offset based on the relocation offset and the data offset from the text section. If the relocation goes outside the data section, it's not position independent. So let's raise an error for that case. The access is inside the data section. but the accessed memory may be inside the text or data, so I'm determining the correct section and then getting the original address. The left shift is used to follow the Yasl file format, where the last bit is the section indicator. And yes, there is a bug since I'm accessing an address from the text section. It should be always fetched from data, and this will be fixed later. Then I started compiling and fixing errors, mainly adding PC relative relocations to skipped ones. I also had to cross-skip data and other relocations. And it seems that relocations for the first module are done. Let's append the text and data for the module. And I shared with you one of the errors. Everything was working. And after one recompilation, libOpenCM3 symbols stopped to be positioned independent. Believe me, I was struggling with that issue for a long time. In the future I will discover that it was related to external modules. Then I added copying the original ELF file to backup, since if MKImage fails, CMake is removing the original file, as MKImage generation is one of the steps of building it. And I added stripping since I left debugging symbols inside the toolchain. Another part of relocation processing. Since I changed the original offset table, I introduced my own index counters. And I have to fix the offset table access inside the text section. And probably also inside data for code in RAM. But I will investigate that in the future. Of course, when the issue will occur. It will be easy to catch because it will fail on MKImage generation. Then I started implementing symbol tables processing for Yasl file. According to Yasl format, I'm keeping imported and exported symbols tables separately. And the last step is building binary image, which in fact is just a realization of data. This step mainly follows format description from theoretical section. You could rewind that video or check it on GitHub website for that project. Some information is not needed right now. They were planned for the future use, so I filled them with some dummy values. Then I'm filtering relocations to correctly fill them. To put it right, I made a mess with external exported relocations. Now I suspect that there is no such thing. They are just same type of relocations, which are symbol table relocations. I will correct that in the next episode. Then I added code to serialize symbol tables. Data symbols must be fixed, similarly to data relocations to base on data start address. Important here is alignment. Otherwise, it will make harder to process inside loader. Thanks to that, I can just cast memory to structs. Same for relocation tables. Since I'm doing only loader part, I can't have symbol table relocations imported nor exported. So I drop them for now. And to be clear, main symbol is not relocation. It's just symbol, which can be exported for loader purposes. Let's add them to the output file. I added 16-byte alignment for code in Yasl format, but I think it's more than enough. This needs to be investigated. I think it's all for MKImage for now. The actual loader implementation I started from parsing Yasl header file. That was the simplest thing that I knew how to start. Since I followed a specific memory layout and alignments for file format, I can just map raw memory into structures. I added printers for enums for easier debugging and correctness verification. Then I added logger, which basically is print switchable on compile time flags. Simple and enough. Next, I made some corresponding changes in CMake. You may be interested how I know that module starts at that address. That's why I added truncation of binary, so it is flash memory start plus 64 kilobytes. I had a bug in local relocations. I added each of them, but I overridden their data. It's not visible on the video, but I was recompiling very often, which was revealing bugs, one after another. If I didn't remove those parts, this video would take days to watch, not minutes. And this video is going to be long enough without. Now you can see how much stuff is contained in a simple application that just prints text. Those symbols and relocations are for hardware and standard libraries initialization. I did some cleaning for the script and moved on to CMake War for adding flux propagation for Yasld that depends on the architecture. Here comes the rain again.
Oh boy, here we go again. Yeah, I'm out.
Yeah, sorry. I can't listen to another one either.
But since I still hadn't tracked that issue, I removed everything and rebuilt as it was helping. And clearly something went wrong. Instead of printing the header, my code jumped to address 0, which is not even in the memory map. I disassembled my awesome loader which couldn't even print. The main function seems fine, but if you look for some loader symbols, you can see that it's not dump code. It's ARM, which is not even supported by cortex-m 0+. It seems I forgot to add the CPU architecture to Yasld flags. I also checked that I added the wrong flag to enable the logger. And now, the moment of truth. Yeah, the first task is done correctly by Yasld. Let's print out the rest of the things from the header. It's for verification of the image and parser. And it seems fine. Let's fix that libopencm3 issue. If I use execute process instead of custom target, CMake will build it only once. Then I again improved logging in the MKImage script and started parser implementation. The header might be just read from memory as it is, but relocation and symbol tables require logic to parse. The parser requires using symbol table parsers, local symbol table data relocation parsers, basically the serializers for the YASI format. Nothing very interesting for now. As a starting implementation, I'm just casting raw flash memory. This needs to be changed in the future episodes when I will need to execute from unmapped memories, like SD cards, or maybe network or USB. We will see. I'm speeding up that part. If you are interested, just check the code on GitHub. It's simple. You can get link and branch for that part from the description. Since I'm using C++, not C, I use its powers and introduce iterators for tables to support range-based loops. Thanks to the fact that MKImage prepares the file for dynamic loader, its task is mainly to parse what MKImage produced. Then only perform necessary relocations that MKImage can't know, and the job is done. With all the serializers ready, let's go back to the parser. It parses sections one after another, and for verification, logs them to the console. The values looks legit. In the meantime, I fixed the symbols table size to contain the number of symbols, not its size. Attention please. This is the part for which that episode was created. The loader must use dynamic allocation, or statically allocated buffers, which are able to keep offset tables and data sections in RAM memory. I mean data sections because it's data and VSS. I added functors to allow users to provide implementations of allocators for them. I am using embedded utility libraries, which is my other project. EOL function is a memory-efficient std function implementation without heap usage for arguments. The executable must know its starting point where its code exists and the offset table. One of my goals was to keep the main function to its known definition. So, the execute function contains an arguments table, which is filled by the runtime system. The call main function will be an assembly function to execute the module. It's easier to implement that in raw assembly than in higher languages. It's kinda low level because it has to manipulate registers. I did some housekeeping of CMakes for latest changes, such as introducing embedded utility libraries. I split the building of libopencm3 versions since they are used by different projects. This was the main root cause why libopencm3 was built incorrectly. I split the building of libopencm3 versions, since they are used by different projects. Now the test host can compile only the regular version of that library, and modules compile the position-independent one for their purposes. Nothing is broken, so let's continue with loader implementation. I created the assembly file in a separate package, since it is architecture dependent. The rest of the code should work on any architecture, and its implementation is simple. It just pushes the current state to the stack to be able to return from the module. It fills the R9 register to point the offset table, and it jumps. This assembly that you see is a fixed version. The first one contained a bug that took me days, really days, of debugging. I will share with you details about that bug at the end of the video. Those host implementations are just stubs. They are used to write and run unit tests on local machine. This is a concept from my video about hardware abstraction layer. Since the executable implementation is ready, let's continue with the loader implementation. We need methods for searching symbols and processing relocations. I did start an initialization in the constructor. Actual logic for executable loading starts with processing the header. We already have a separate abstraction for that. Of course, the file must be verified if we got a Yasl file. The loading executable function returns an optional executable object. If it wasn't created, something failed. Error codes will be added in the future. Now I'm doing proof of concept. Then I use the parser to determine the rest of the necessary information from the file. The offset table must be allocated for all symbol table and local relocations. The first version supports only execution in place from flash memory, so I link text to variable. But in the future I want to add possibility to copy whole module to RAM and execute from there. The process.Data function allocates memory for data and BSS sections. Then it copies data to memory and zeros BSS section. Next, I added a logic algorithm for the rest, which is parsing symbol table relocations, processing relocations itself, searching main symbol, and returning executable if found. As I said, symbol table relocations are not allowed without full linker implementation. But local relocations must be implemented. They are simple. I searched for section to get its start address, then I filled offset table with sum of start address and encoded offset from Yasl file. Data relocations are a little bit more complex, but still it's not rocket science. It's just calculation of target and source addresses, and then setting value inside target to source address. The host executable has to use loader implementation, since for now it used only parser from dynamic loader. I added some arguments to be passed to main. I used some parser functionalities that I didn't implement yet. And I forgot to implement symbol searching. This just iterates over symbol table and compares names. If found, it returns base address, which is start of text or data section, plus offset from symbol table. The module was loaded, but then crashed with jump to address 0. I'm showing you one of the debugging sessions because I used a feature called add symbol file, which allows loading more than one symbol source. I had to manually set the text section for the module, since it was loaded at runtime by the dynamic loader. It seemed that the main execution started and crashed. Jump was executed to address inside register R2, which seems to hold an ARM function address. I know that because the thumb version should be offsetted by 1, so I fixed the flags again, this time for the modules. And now it works. Let's implement test for that, which just verifies that hello world was sent on UART. Then I temporarily introduced a bug to check that the test was working. Similarly, I added a test to verify that incorrect files are rejected by the loader. The next text verifies that the module can exit to its runner. It's a simple program. It gets numbers as arguments and returns their sum. Let's stick to integers in that test, since for microcontrollers without hardware floating point, libgcc is used, which may reveal new bugs, because libgcc must be also position independent. And this is that test. It also calculates the sum, but this time of float values. And it uses a function with variadic arguments, which reveal the hardest to debug issue, due to type promotion. I will talk about it after the outro. That's all for today, except for a lot of places in environment and building system where you can introduce bugs, and a lot of stuff that had to be prepared before actual implementation. It required a lot of work, but actual concept is easy. Once again, sorry that this episode took me so long. Hopefully the next episode will be faster. Some parts, like preparing the toolchain, preparing environment, preparing project, also tracking the hardest to find bugs, took me a long time. And I made some issues during recording, so I had to record that twice. Another thing is that I'm doing that project in my free time, which is of course limited. I think that next part will cover dynamic linking. If you have any comments or questions, don't hesitate to write them. I hope you get some value from my hard work, and I will be rewarded with likes. For those interested, here is the main sponsor of that episode. Stack alignment bug. Let's see the original implementation of call9 assembly function and compare it with the new one. The new version seems to push and pop register R5 without any purpose. And the reason for that is described in the shared stack usage rule. For 32-bit ARM processor, the stack pointer must be aligned to at least 8 bytes. And GCC assumes that this is met. My first code broke that rule, which led to undefined but stable issues when accessing 8-byte types. That's why some usages of print during implementation were printing wrong values, and why the test with variadic arguments was crashing. Floats are 4-byte types, but variadic arguments promote them to 8 bytes. I investigated that inside GDB using possibility of calling functions from GDB itself, and checking what's going on with registers, memory, stack pointers, and I saw that some values weren't properly read, but I didn't know why. It took me a while to compare it with working code, and then I realized that the issue occurred on stack pointer aligned to 4 bytes when accessing 8-byte type. So I started digging into ARM documentation, and that was it. Thanks for today. I hope to see you soon, not like this time. Bye!